far as the topic is concerned, my talk is connected to the first talk that we had today, Professor Moorman's talk, although it is temporarily separated from it. So it's going to be about methods for constructing points from meritopological structures again. And today, in the first session, we heard about two methods, but there are a lot of them. So in the last 100 years, many methods for constructing points from different kinds of meritopological basic structures have been proposed by various authors. There are lots of Polish names among them, some names from people sitting here at the moment. What I want to do in this talk is to take a step back and look at these methods from the distance and say something more general about them. So the first observation I want to make is that many of these methods are tailor-made for specific kinds of structures that satisfy very specific axioms. A frequent assumption is, for example, that the structures are atomless. And there are a couple of objections against these strong assumptions about the underlying basic structures. For example, Russell, in the analysis of matter, objected that we should be neutral about whether the basic structure is atomistic or atomless. That's nothing that we know about. We shouldn't presuppose that. In the words of Jeremy Butterfield, because the cure would be as bad as the disease. The assumption of atomlessness would be just as implausible and bad as positing unextended points, mereological atoms, from the start. So the question that arises from these objections is whether there are point construction methods which are neutral with respect to the underlying basic structures, which are generally adequate in the sense that they work for all kinds of relevant structures that we might use as input for our construction methods. So in particular, the method should work both for finite and infinite structures, both for atomistic and atomless structures, and both for discrete and continuous structures. And Thomas, that concerns your question from yesterday. We can really explicitly distinguish these things. Sometimes physicists say atomistic when they mean discrete. We can't separate this. So the goal of my talk is to evaluate some prime examples of point representation or point construction methods with respect to general adequacy. And I will give answers to the following three questions. The first question is, what exactly is a point construction method in the first place? The second question is, under which conditions can we say that a point construction method is generally adequate? The basic idea is what I just said, but you can make it formally precise. That's what I'm going to do. And then I will answer the question whether there are any general adequate point construction methods in that sense. Okay, so I'll just give you the answer to the first question, what point representation methods are. And you can write down the definition quite precisely, but I think it's better to explain it, to explain the basic idea. So the idea is that we are given a class of pre-mereological structures that can be enriched by additional relations and operations, for example, topological ones. Then we have a triple of functions such that for every basic structure, the first function, which is here called PT, assigns to the given structure a set of points. And this will be done by means of some definition of the notion of point in, by means of some logical construction. The second function is a correlation function, which tells us which points in the point space belonging to the given structure, which points correspond to which element of the basic structure. And this is the function cor, which gives 0 or 1, depending on whether the point can be seen as being in that element or not. So this gives us representatives of the old elements. And then finally we have the third component, which is just a mapping the whole structured set, so the set of basic elements together with all the relations to structure of the same type, which is atomistic. So that's the basic idea of what the point representation method is. Now, the question under which conditions a point representation method is generally adequate is a bit more complicated to explain, so I'll split that into several components. And I first want to define what relative adequacy is. So imagine you get a subset of sigma structures, call it sigma star, and you want to know what it means whether a point construction method is adequate for those chosen structures in the smaller set. And that can be defined as follows. This is something that can be extracted from the literature. I say that the point construction method is adequate for structures of a certain type, subtype of sigma star, just in case for every structure of that type, the mapping PT sigma, which is induced by the correlation mapping here, which assigns to the original basic entities their representatives in the constructed atomistic structure, is an embedding of the original structure into the atomistic structure which is constructed. So that's the first thing. It has to be, the old structure has to be contained in the new structure in a well-behaved way. That's the idea. And the second condition goes back to a paper by Professor Moorman from 2009. And it says that if a structure is already atomistic, so if the input for our method has already atoms, then the point construction method should not change anything. It shouldn't add new points to the ones we already have if the structure is atomistic. So there should be an isomorphism between the structure we start with and the constructed structure. So that's a kind of idempotence condition. And the first one can be called embedding condition. Well, now to say something more specific, I have to introduce a bit of meritopology. So the classes of structures, the kinds of structures I want to analyze a bit further in this talk are weak meritopological structure, what I call weak meritopological structures. They are just classical mereological structures enriched by an additional relation of interior parted, for which certain formal conditions hold. So interior parted has to imply parted, and it has to be well behaved in this sense, and it should be distributive with respect to the product, and everything is contained in the universe, and it is dense. This condition is a bit strong. It's the strongest and probably most implausible or objectionable of these conditions, but it's not too strong, as we will see if we look at examples for these structures. So prime examples for weak meritopological structures are the regular open subsets of a topological manifold, where the interior parted relation is interpreted in the sense written down here. So the closure of a set is in the interior of the other set, then the first is an interior part of the other one. So that's an atomless structure, weak meritopological structure. But there are also atomistic structures which satisfy these axioms and are continuous in a certain sense that Thomas mentioned yesterday. So you could also just use all the subsets, apart from the empty one, of a given topological manifold and use the subset relation as the parted relation and the relation of interior parted as we defined it in the first case. But now we have all subsets of the space as relator. So that would be also an example. And there are also atomistic and discrete structures that satisfy these axioms. For example, if we take any set of points and we take the power set algebra over that set and use just the subset relation as interior parted, we get something like a discrete meritopological structure. So it's very similar to what we have in classical topology, where the open sets can be chosen as all the subsets, then we have a discrete space. And we can do something similar here. More generic examples are these, for example, the structures that Grzegorczyk uses, or proximity spaces, all satisfy these conditions. Also Smith's meritopology, although this is the interior parted relation is a different intended meaning than here, they satisfy the axioms as well. And also Röper's so-called region-based topologies, they all satisfy this. So this is a very large general class of structures. So we are not excluding too many structures from the start. There's a lot of things in there, and many of them are pathological in a certain sense. But we'll deal about that later. Just an important fact to note at this stage is that every atomistic weak meritopological structure induces a topological space. Just take the atoms of the structure as the points of the space and then use the notion of interior parted to define which sets of points count as open. Namely those sets of points where the sum is its own interior, and an interior operator can be defined for weak meritopological structures. So this is something that we're going to use later. So just keep that in mind. And it's useful to add an additional component, namely a property of limitedness, as we could say, and use very intuitive, simple conditions for this notion of limitedness. So if one object is limited and something is contained in it, then that is also limited, and two limited things have a limited union. So that's something that we will also use. So it's, in a certain sense, not purely meritopological, but meritopological plus a notion of boundedness or limitedness that we use. And for these kinds of structures, for these kinds of meritopological structures, we can define what general adequacy is. So I call a point construction method generally adequate, just in case it is adequate, relatively adequate for the following class of structures, which I call WB for well-behaved. So this class contains all the finite discrete structures of that kind, or infinite discrete, atomistic continuous, and atomless structures. And now there are a lot of terms that are unclear, probably. So what does discrete and continuous mean, for example? that can be explained. I won't go into details, but you can use the properties of the topological space induced by an atomistic meritopological structure to define what discreteness and continuity are. So in particular, an atomistic weak meritopological structure with information about limitedness is continuous just in case its induced topological space is a topological manifold, so as a topological space locally isomorphic to Euclidean space. Another unclear notion is the predicate well-behaved. So what does that mean? I won't define this. I just have to assume necessary conditions for well-behavedness. And I have to use these conditions. For atomistic structures, I require that they are well-behaved only if those regions count as limited that are part of compact regions where compactness can be defined by reference to the underlying topological space which exists because it's atomistic. And for atomistic continuous structures we need a further condition, namely that interior partude really reflects the intended meaning, namely that the closure of X is part of the interior of Y. So that's well-behavedness for atomistic structures, in particular for atomistic continuous structures. And for atomless structures, the conditions are a bit more complicated. And I won't go into the details right now. Just think of them as additional conditions which carve out those atomless weak meritopological structures which are not too pathological. Okay, well, so far we have answered the first and second question. Now the question is, are there any generally adequate point representation methods in that sense, defined as I showed to you? And I want to look at three prominent examples, namely the ultrafilter method, where we use ultrafilters as points, which has been mentioned by Professor Mormon today, and where he said that this is probably not the best thing to use. And the notion of the completely prime filter method, which is equivalent to using frame homomorphisms that were used by Professor Mormon and proposed as the adequate construction of points for Heyting algebras. And the third is the use of maximal round filters as points. And we'll just look at them one by one. So the first method just uses ultrafilters as points. The idea is very natural. It suggests itself really to just use Stone's representation theorem and think, okay, well, we have this result about Boolean algebras that can be embedded into atomistic complete Boolean algebras, so why not just use that method? And Skirms, for example, explicitly does so in his paper on Russell's work. But it turns out that although the ultrafilter method satisfies the embedding condition for all well-behaved structures, it violates the idempotence conditions for infinite atomistic structures. And the reason is rather simple. There are last piece of paper, sorry. You can imagine that there are just too many ultrafilters, in particular free ultrafilters in atomistic structures. Think of the Euclidean plane and think of a chain of regions that in some sense vanishes to infinity. And then you use that chain to generate an ultrafilter from it, and it will be an ultrafilter that does not converge to any point intuitively, right? But it is an ultrafilter. So there are, in some sense, ultrafilters that are not representatives of points. So it's no wonder that this method doesn't properly work. And this idea is really captured by the definitions I gave. So you can really rigorously prove that that the ultrafilter method is not generally adequate. So we can cross it out from our list. What about completely prime filters? Now, since using all ultrafilters is a bit too liberal, because there are ultrafilters that do not intuitively correspond to points, and which is reflected by the violation of the formal adequacy conditions I gave, it's a natural idea to just select certain ultrafilters, special ultrafilters that satisfy additional conditions. And one thing we could do is to use completely prime filters. All completely prime filters are ultrafilters, but not vice versa. And this is totally common in point-free topology, and it is used. This method is used to establish the duality between sober spaces and spatial locales in that area. So why not use that? And Professor Mammon in the first talk suggested to do this, and I want to question this method because of the following result, which is not surprising or very new, but still important. So the completely prime filter method does not have the problem that the ultrafilter method had. So it satisfies the idempotence condition for well-behaved structures. So if we give an atomistic structure as input, then it will change nothing. The constructed structure will be isomorphic. But it violates the embedding condition for atomless meritopological structures of the kind that I'm talking about. And the problem here is the problem of prime elements. The existence of completely prime filters presupposes the existence of certain elements in the underlying algebra. So if we look at the Heiting mereological structure, then we can prove that either the set of atoms has the same cardinality as the set of points of completely prime filters we can construct using the completely prime filter method, or the Heiting mereological structure violates the weak supplementation principle. So what's going on here? What completely prime filters do is they presuppose that there is an element in the underlying algebra which is can be intuitively thought of as the whole space where one point is deleted. And in some sense, this is, smuggling in points via a bit of a trick. So the problem is now that if we have weak supplementation, so if we have complements in our algebra, then we get the point, and the existence of a completely prime filter presupposes the existence of a prime element, and that leads to the existence of a point. So we already have the points if we can construct them. So the only way we can escape this problem is to reject weak supplementation, but I think that this is not a viable way to go, because I think weak supplementation is really essential for partite relations, and it doesn't make any sense to think of the whole universe where one point is missing, but there's nothing that makes up the difference. That's philosophically implausible to me. So this implausibility is again reflected by the formal adequacy conditions I gave, but that could be discussed, of course, whether this is good or bad. We can cross that method too, I would say, and there's only one left that I want to talk about, namely the method using maximal limited round filters. So the idea here is that we add additional conditions on filters that we can use as representatives of points. We say that the filter is round just in case every element of the filter has another element in the filter which is its interior part. So in some sense, within the filter, the interior part of the relation is gunky. And a filter is limited if it contains a limited element, and a limited round filter is maximal if there is no other limited round filter properly containing it. And that method is proposed by Roeper in his huge paper from 1997, and also picked up by Professor Morman in, that should be 2009 in the Wittgenstein Symposium proceedings. And Roeper proves a very fascinating theorem about the maximal round filter method. He shows, using that method, that there is a categorical equivalence between Roeper structures, so meritopological structures of the type I'm talking about, of a special subtype, and locally complex Hausdorff spaces. You can really go both ways. That's more or less the same. But this does not actually tell us that this method is generally adequate. That doesn't follow. There are several technical problems, but the main problem is that there are no atomistic continuous Roeper structures. So this result about Roeper structures does not tell us that the method is generally adequate, because a generally adequate method has also to must also be able to deal with continuous atomistic structures, and there are just none in Roeper's system. However, one can do the proof and look at the details and check that this is not the problem. So the culprit is not the method of using maximal round filters. The culprit is rather that Roeper's axiomatization is stronger than probably necessary for the purposes I'm interested in, not for his. So the positive result of my talk is that the maximal round filter method is indeed generally adequate. And a question I'm interested in, and I would like to discuss with you probably, is whether there are other non-equivalent point construction methods that are also generally adequate. I don't know, but let's see. Yeah, that's something for further research. Thank you.